Hi everyone, this is the ML Bull, and this is part 3 of our series on using AI ML techniques to try and weasel a few points out of the FX market. So just way of introduction, I'm the ML Bull, and I've been trading FX for about 20 years in different capacities, originally using more traditional analytical type methods, and then more recently, of course, using AI ML, the last 5 years or so. I have multiple technical degrees, including a Bachelor of Engineering, lots of certificates in machine learning, etc. And it's techniques I've been using for a long time. Basically, you're not going to get mega rich with a quick fire FX trading strategy. However, there are techniques that do work, and I'm trying to share some of the pitfalls I've learned over the years, because you will go down the rabbit hole, and I'll try and keep you out of it. So the disclaimer: this is in no way financial advice. This is intended as a lesson in using AI ML and applying it to the FX market. You have to develop your own systems and your own techniques and your own appetite for risk. So this is in no way financial advice. It doesn't advocate for any specific strategy or to trade FX as a positive return device. All right, so let's get into it. So in our first video or episode, we looked at a kind of a hello world example of using ML, and we created a almost completely useless system that is good for not very much at all. So, and then in the second episode, we added to that a little bit. We saw some of the gaps and we improved it a lot, but we're still really not much better than guessing what the output is. So we can't really move on and look at what's next without taking the covers off the approach we had. So the technique we used is probably the most simple approach, which is logistic regression. And we need to see what's going on under the covers to go to the next level. So this video is going to be about a little bit of the understanding of logistic regression and really what it's all about. So Wikipedia defines it as a logistic model or a logic model that looks at the probability of event taking place, and it uses log odds to produce a probability. So you have a set of inputs and it creates an output which is a 1 or a 0. And it does that using actually some pretty simple math. It's not overly complicated, but what we need to understand is some of the fundamentals of how that works, so we can see where the next set of gaps are. All right, so let's take a look. So what's happening under the covers here is really the basis of a very simple equation, which is the output is some weight, W, times the value. So in our earlier model, our Hello World model, we used the price from the last 4 time periods. So it's a weight times the last close price, a different weight times the close price before that, and so on. And it adds them all up and it gives you a number. Now it's important to remember this is a simple weight times a simple value. This is not some super complicated system. Now, how it derives this and learns, we're going to talk about log losses and the other things, and for our purposes that's not so critical, at least not at this point. We might get to it later, but you need to know that this is a very simple equation of each feature times a weight, and then they're just added together. And logistic regression then adds this sigmoid function, which is this nice curve function that just kind of sets everything between 0 and 1, so we can call it a probability. So it's a simple weight times a simple feature value. So as you would expect, there's some things that can go horribly wrong. If your feature values are very different, then a small movement in the weight can massively impact one feature but less on another, so it gets a bit out of whack. And then the second big insight to learn here is this is fundamentally a straight line. It's a linear equation. It's very, very simple. And so while the learning process is complicated, the output isn't. And then we just add this sigmoid function to basically ramp us between 0 and 1 and create this probability of something happening. So the message here is don't be overwhelmed by these equations. They're not complicated. And to use them, you just need to remember that it is this simple weight times the feature value. And if you think about what's going on with our numbers, how they change over time, you're going to start to see that there's some problems that can develop with how we're doing things. All right, so let's see this in practice. Let's see this in action. And this is the same code we've always used. There's nothing changed here. We're just going to import our raw data. If you remember our 60-minute time frame, and it's exactly the same as we've had previously, no change. Then we're going to create our time-shifted features, xt1, xt2, etc. But the difference here is we're just going to limit it to 2 features. You see I've just commented out the third and the fourth. And that's because a bit later on we're going to try and graph this. And with 2 features we can just do it nice and neat on an x and y axis. With 4 features there's a lot of dimensions going on. It gets a bit messy. So we're just going to limit this example to 2 features. It's going to mean our answers are even more rubbish than they were before, but it's going to illustrate the point. So let's go ahead and run that. And then what we're going to do here is create our training and validation data sets, and no change here, except of course we're just limiting it to the 2 features. The class weights, if you remember last episode, we went into how class weights are so important, and this is where we're going to do something different. So what's happening here is we are going to train the logistic regression algorithm on a range. So you see we're going to loop through all values between 0 and 500, and then we're going to go 500 to 1000, 1000 to 1500. So we're going to take 500 values. We're going to fit our linear regression algorithm, and then we're going to calculate the lines that it produces, the intercept, the coefficients, etc., what the feature values are. And what we're hoping to do is calculate the probability ourselves using the formula that we just looked at, which is this coefficient or weight times the feature values plus the intercept, because if you remember there's an intercept. And then what we're going to do is actually have logistic regression algorithm predict that, and then we should get the same values. So let's see what happens when we run this. So the last value in each section, you can see the x1 and x2 feature values, the y value is 0, as in at this specific number 100, index 100, that specific value, there wasn't a the price going more than 200 points. And what we're able to do is get the different weights and calculate that probability. Remember, we have to wrap it in a sigmoid, so it gives us that, and then compare it with what logistic regression gives us. And you can see those numbers are the same. So that means we're calculating it the right way. We've got a good handle on what's going on here, and our math is adding up. And this is important to do these types of exercises, even if it seems a bit redundant, because it makes sure that you're calculating it properly. It makes sure you're thinking about it properly. Now, as it loops through each 500, what you can see here is the weights change quite dramatically as we go. At the end, 0.8, 0.3, 0.5. With each 500, it changes quite a lot. And that should be giving us some insights into how stable our system is here. And because it can move so much with very little data change, it should tell you that something's not necessarily wrong and off, but something's going to become unstable. So we're starting to see that our data might be a little bit unstable. This might not work. We're getting some big swings in our prices over time, so those weights aren't going to add up quite right. we are getting some big weight changes, which starts to tell you that we may not be using the best technique. So let's just have another deeper dive on that. And what we're going to do is plot our data with the decision boundary. So above means it's 1, we're predicting that it will in fact go up, and below we're predicting a 0, i.e. it's not going to go up 200 points. And we do that with the same techniques we used before. We fit our data, we get the weights, the intercept, the gradients of curves, we pull out X and Y, and we're going to plot them. So I've got a function here to fit and get the model parameters for any set of X and Y, and then we're going to plot the decision boundary, which means breaking it down to a 1 or a 0 and doing a scatter plot and showing where they fit. Now ideally you should see some type of pattern, you should be able to visualize it. And if it's all one side and the other side within a straight line decision boundary makes sense. If it's in little groupings, then you need to more draw circles around those, so we can use different techniques, particularly anomaly detection, to create these little bundles or groupings of ones and zeros. Or if it's a very complicated line, we can use other techniques such as deep learning to really create some very intricate decision boundaries. But if we set our data from all values and then we fit our parameters and then we plot, what we're going to get is this curve. Eventually, there we are. So there's our data, and you can kind of see that the red line, the ones, the X's, they are pretty well distributed. We've drawn a line here that's kind of 2/3 of the way up. So what we're saying is everything above that is a 1, everything below that is going to be a 0. But what actually happens is not that. It's far more distributed. And it very well may be that there's nothing in these two input variables, X1 and X2, or the price 1 period ago and the price 2 periods ago, that can actually tell us what is going to happen in the future. And that may be what we're looking at here. And because it's so uniform, we're seeing those big fluctuations in the weights. Because if you can see over time too, the price 0.55 up to 0.9, of course if you remember this is the Aussie US, and what they're telling you is these big numbers, that's almost twice as much. And remember, we have a simple weight times the price value, and there's these big swings in the price value over time, which is normal in FX, but it does tell us that this model, this approach has got some gaps. So let's so here's some other values, other decision boundaries where I've limited the data. So all data up here on the left, that's what we saw before. If I just do a very small subset, so the first 10,000, we really get this nonsensical decision boundary. It just doesn't make any sense at all. Again, here on the bottom right, I've limited the data to a smaller subset. Bit of a bigger subset here, and it's really moved the decision boundary way down, and that's probably a function of how the price is changing over time. And what that's telling us is, data is becoming nonsensical. This approach has got some gaps, and we're going to have to rethink how we're looking at some of these data points. And that's going to be the subject of the next video, which is going to be more how we normalize this data and how we look at it to try and bring these things closer together and make these weights work more effectively. And that's a process called normalization we'll be looking at next time. All right, so that's the video for today. The show notes have all the code in GitHub. There's Medium articles you can refer to, etc. So feel free to review all that, and I thank everyone for their time.